Welcome to whoever is out there in the audience. As Anne mentioned, we're going to be talking a little bit about analyzing data from Kinarm standard tests. And again, as Anne mentioned, it's really about what data is there. We don't tell people how to do their science because there's lots of different ways and applications that are out there, but it's important that people understand what's there and what's possible. I'm not sure how many of you were around the last time I was out in Calgary. So if so, there's probably a couple slides that might look familiar, but if not, I'll just get into this. And normally I would have given this is part of the training I give when I go and install with new customers. And there's normally an initial talk related to the actual tests themselves, but since I know you guys have been using those for a long time, it's really about the analysis and review. And I like to point out a couple things that after you've collected data, there's a couple different things you can do. And the first one is to remind people about qualitative analysis, and that this is actually useful in the sense that you can replay the subject behavior afterwards to get a sense of what actually happened when your subjects ran their Kinarm standard test. And the other part, of course, is quantitative analysis. And so I'll mention a little bit about printing reports, but a bit more on the actual scores that you can get out in CSV files, and that you can actually go beyond that if you want to. In terms of reviewing and replaying task behavior, I hope that all of you are familiar with Dexterity Explorer. This is the free software that we offer so people can review their data, make presentations. It's available for both Mac and Windows. And what you do is within Dexterity Explorer, you can select a subject, you then can select an exam, and you click the play button and you can watch and see what they actually did during the task. In terms of being able to do that, of course, one wants to be able to share exams, so you have your data all presumably on your Dexterity computer in your lab, and you need to get it out to, say, a coworker, colleague. Simplest way, if you want to do just a single exam, is you can select a subject, select an exam, and then you right-click and you can export it. That single exam that was maybe emailed to you, you can actually just drag and drop it for an instant replay onto Dexterity Explorer, and away you can go and you can watch what happens. There are a number of other exporting methods, and which one you use depends on what you're trying to do. But you can export files by day for a single subject. You can export by the whole subject, or you can export by filters. So for example, you might be running a particular study, or maybe you're interested in a particular task type. And once you've exported all that data, you can import it into another database, which allows you to manage your data locally, say on your laptop or in your office. In terms of quantitative, the first option that we look at for quantitative analysis is looking at reports. This provides a summary of subject's performance, and you can create these both within Dexterity, but also Dexterity Explorer. So again, if you've exported your data and it's sitting on your laptop, you can go in and generate reports. You select the subject, select the exam, and then click on the icon that will turn a nice color there and allow you to generate a report. I don't know if you've all spent much time looking at reports, but they all contain similar types of information. Each standard report starts at a header. It contains subject information, task name, plot of behavior, the task score, and then the subject scores. And with the subject scores, you also end up with the 5 to 95% range, which provides you an indication of how well did this subject do. And it's important, and I'll talk a bit more in a minute, that these typical ranges are based upon normative models that we generate. So this accounts for things like age, sex, and handedness. A standard report for a single exam is useful, but it's a piece of paper, and it's hard to do an analysis with numbers on a piece of paper, particularly because often when you're doing research, what you're really interested in is meta-analysis. So what do I mean by that? Well, I'm going to give a couple examples. Maybe you're interested in whether or not a treatment has some effect. So you want to measure uh, performance or behavior before giving some type of therapy, and then look at it afterwards to ask the question, did my therapy help? You might be interested in comparing two subpopulations. And so, for example, people with a migraine versus people with a stroke. Or you might just be looking at a new population, and new in the sense that hasn't been studied yet with KST. And the point I'm getting at with each of these types of questions is that you need to analyze the data from many subjects. So that's what I mean by meta-analysis. It's not just looking at a single subject scores. You need to put a lot of them together. So how do you get that data? Well, you access it by exporting it into CSV files. CSV, by the way, stands for comma separated value files. These are it's a standard file format. It can be opened up in spreadsheets or statistical packages or MATLAB. And from within Dexterity or Dexterity Explorer, you click on the File button and you choose Export Analysis. And there'll be a couple other dialogues, but you end up with a file, which this example here I've shown you is what it looks like when it's loaded into Excel. And it has a significant amount of information in there. Each row in the CSV file is going to be for a single exam, and each column is going to contain different data. And we deliberately put a lot of information in here to make sure that you have access to the information you need to analyze. So the first 15 or so columns are dealing with information about the individual exam. So what was the subject, what was their age, what was their sex, what was the exam type. And then there's a whole lot of columns that deal with the raw parameter values, followed by the z-scores, followed by the percentiles. If you're going to analyze group data, so you're going to do this meta-analysis, there are a number of challenges that you need to be aware of. And the first challenge is that there are age and or sex effects. So this example, this slide, I've plotted reaction time versus age. This is from the visually guided reaching task. This is all healthy controls. And what's important is look at people with reaction times of 350 milliseconds. If I'm 20 years old, that means I'm actually pretty slow. If I'm 80 years old, that means I'm pretty fast. And my point being that if you just took the raw scores for reaction time, you can't group them together. You can't do a group analysis on here because 350 milliseconds means something very different depending on how old you are. So this is a challenge that you need to deal with somehow. Another issue is that many of the parameters are not normally distributed. The example I give here is the ratio of time for trails B over trails A. I chose this particular example because this is well known in the literature. The trail making task has been around for decades, and it's well known that there is this highly skewed distribution. And that creates a problem if you're planning or hoping to use parametric tests, because they, of course, assume that the underlying data follows a normal distribution. A third problem, and this is not so much dealing with the numbers, but rather with interpreting these numbers, is what does it mean? So for example, if I were to look at visually guided reaching, and I think of the parameter initial direction angle, and I say, hey, this subject got 3 degrees. Well, what does that mean? How many of you know if that's good or bad? I have no clue. Uh, I mean, if you go through all of our tasks and all of our parameters, there's well over 100 parameters. They all have different units. They've all got different ranges of what's normal. And so it's virtually impossible for someone to memorize what are the normal ranges for each of these parameters, which then makes it a challenge for interpretation. These issues, luckily, can all be dealt with. And the solution that we've taken, which we're certainly by no means the first group to go down this path, is we convert things to Z-scores. For those of you who have some experience with statistics, you will maybe have heard of Z-scores before. Again, we did not create this definition. It's something that's been out in the field for a long time. And what a Z-score means is it indicates how many standard deviations away from the mean a subject's performance is. So a Z-score of 1 means that you are 1 standard deviation away from the mean. A Z-score of 4 means you're 4 standard deviations above the mean. So if you can convert to Z-scores, that solves a number of problems. And one of the key things is that the methods that we use to convert our raw scores to Z-scores account for the effects of sex, age, and handedness. So that means that if I go back to that example I had of 350 millisecond reaction time for visually guided reaching, when I convert those to Z-scores, if I was a 20-year-old, well, they're going to have a Z-score about maybe -1 because they're faster than the mean for a 20-year-old. If I look at the 80-year-old, they might have a Z-score of, sorry, I got that backwards. The 20-year-old would have a Z-score of +1, the 80-year-old would have a Z-score of -1. And the point being that it's in relation to the mean, and we're accounting for the age effects. Our methodology for converting to Z-scores also accounts for skew, so it removes the skew in the data set, so we ensure that everything is normally distributed. And of course, the original reason for creating Z-scores is that it provides a consistent interpretation. So any parameter, if I say, this person has a Z-score of 2, that means they're 2 standard deviations away from the mean. I don't have to memorize different ranges of what's normal or anything else. I already know what it is because now there's just one set of scoring systems I need to understand, and that's just these Z-scores. I don't want you to worry too much about the details here in terms of how we calculate Z-scores. I just show this because occasionally people want to know, and also to iterate that it is actually a fairly sophisticated process. Again, we deskew the data. We then account for sex, age, and handedness effects. We then can normalize the data, and then we go through an outlier removal process, and then this gets iterated. Obviously, there's a few subtle details that aren't captured here, but this really is providing an overview of the main issues here. And we've spent significant time over the years refining this and, more importantly, verifying and validating this kind of process. Why does it matter? Well, because the algorithm you use can actually have significant impacts on accuracy of the Z-scores that you produce. And I'm going to provide a comparison to what I'm calling the classic binning method, because the classic binning method is one that has been used very often, particularly in the psychological literature, and that's where you bin things by age. I'll give an example where maybe you've got 500 subjects, which is quite a large database, and if you split that evenly across ages, then again, what the classic binning method does is it'll look at all the 20 to 30-year-olds in one bin, and then independently look at the 30 to 40-year-olds, and then independently the 40 to 50-year-olds, and such. And when you take that approach and then you build models, you can then ask afterwards, okay, what's my accuracy or error in my Z-score? And you can see that the particularly as your Z-score gets larger and larger, and even at a Z-score 3, the classic method, the error is very significant. You're already talking well over 1, whereas the method that we use with the multiple linear regression gives you much, much more accurate results. So again, the main point here is that we do verify and validate our methods, and we've been developing these for a long time because it's important for us that our customers have numbers that they can actually trust. I'm going to compare, just to sort of summarize where we're at in terms of these Z-scores here. If you compare raw scores and Z-scores, why would you want to use one or the other? Well, if you're trying to group your data to do some sort of group analysis, you cannot do that with the raw scores. You have to convert to Z-scores because that removes the effects of age, sex, and handedness. If you want to use a statistical test that makes an assumption about normality, then again, for most parameters, you can't use the raw scores. You need to use the Z-score. And although this doesn't affect your statistics in terms of just looking at your data and understanding it, again, Z-scores just provide a huge benefit because they have a consistent meaning across the parameters. Once you've worked with Z-scores, you also will be able to convert to percentiles because, again, that's just a standard one-to-one mapping. In terms of accessing these normative models, right now we do not actually include the Z-scores directly in the reports. As I mentioned earlier, you get these typical ranges, the 5 to 95% normal range. That is based upon the normative models that we use to generate Z-scores. So that typical range there accounts for sex, age, and handedness effects. So if I have 2 different subjects of different ages and I look at their reports, they're going to have different typical ranges there because of their different ages. One of the questions that we got as feedback from our customers after we started introducing Z-scores was they really want to know, did the subject pass the task? So if we look at the parameters in Z-scores, that gives us lots of details, gives us some insight into different parts of behavior for each different task, but it doesn't really necessarily provide an intuitive way to know, did the subject actually do well or not? And particularly, some tasks have just a few parameters, some have several dozen, so you can't come up with some overall, well, if they fail on 2 parameters, then they fail the task. That just doesn't work. To address this issue, we introduced a parameter called the task score, whose goal was really to try to provide an answer. Did the subject fail or not? Because if they pass, I don't really need to look at any more of the details of their parameters. But if I do fail, well, then I might want to dig a bit more. This is what I had mentioned earlier, shows up on the reports is this task score. And it, again, provides increased interpretability of the report. And something that's important, which I'll get to in just a moment, is it's a consistent scoring across the different tasks. In other words, they use the same scale so that a task score of 1 on one task means the same thing as a task score of 1 on another task. Where does task score come from? It's derived from the Z-scores. And in particular, what it does is it measures how far from optimal was the subject's performance. And it's going to use Z-scores as the basis. In general, all parameters that can produce Z-scores contribute to task score. There are some exceptions. I'm not going to go into the details about all of that because that's starting to get quite specific, but we do provide information in our user guide about which parameters are excluded from task score. I mentioned in that last slide that task score is giving a measure on how far away from optimal you are for a Z-score. And that, of course, immediately leads into the next question, because if you start thinking about different parameters, some parameters have their optimal performance at a Z of 0. So for example, hit bias and object hit, whereas others are going to have an optimal at, say, Z of plus infinity. For example, number of objects hit in the object hit task. And so clearly we have to somehow account for that. And you don't need to worry about the details here, but what we do is if the optimal performance is at plus or minus infinity, then we first transform it so that the optimal performance in this new variable called zeta equals 0, so that we always end up dealing with an optimal performance is at 0. If you're interested in the equation for how we derive that, that's also in our user guide. What we end up doing is we end up calculating the root sum square distance. For those who are mathematically inclined, this is also known as the Euclidean distance. That means is you take each of the parameters, you square them, you add up the square of all of those, and then you take the square root. It's difficult to show that in an n-dimensional space, but for a three-dimensional space, you can see what that means here. So if these are Z1, Z2, and Z3, so for 3 of those parameters, if you take the RSS, what you're ending up calculating is actually the distance from one end of the vectors to the other end. What this means is that, again, if we think, or we've defined Z-scores and zeta scores to have their optimal point at Z equals 0, well, that means that the RSS distance would be 0, 2. So again, task scores are measuring how far from optimal was a subject's performance. And because it's a distance metric, it is a one-sided score, so it's always positive. And the scale that we chose is one that will look very familiar to you for the Z-scores and standard deviations. So a task score of 1 encompasses 68.3% of healthy subjects, which is the same percentile that you get for the normal distribution of Z-scores between -1 and 1, and so on. So what's nice about this is, again, you've got a scaling system that is going to be fairly intuitive in the sense that it's the same across all tasks, but it also provides a very similar metric to what you get from the Z-scores. Where do you get task scores? Well, as I mentioned, as I mentioned earlier, they're found in reports, but of course, we also export those as well. So in the CSV file, you get all the raw parameters, you get the Z-score equivalent of those parameters, and you also get the task score. When we were developing the task score, we had actually considered another metric. And this is something that we have called the M-score, and we actually do include it as well. And to understand why, I need to go back a moment and mention that with the task score, it treats all of the parameters equally. So it doesn't pick and choose different ones and weight them differently. It just treats them all equally, which means that if you have highly correlated parameters, you're potentially going to get a bias in the task score, which perhaps weakens its ability to identify abnormal behavior. So the M-score is based on something called the Mahalanobis distance. It's analogous to the RSS distance, but it accounts for parameter correlations. What do I mean, and what's an example? Let's imagine we had two parameters, A and B, that were highly correlated. And if that's the case, and I were to sample subject's behavior on it, so I get maybe a couple hundred data points, I might end up with a plot that looks like this, where if you look at all the little blue crosses, I plotted the performance for each subject on parameter A versus parameter B. And because I said these are highly correlated, of course, you get the cluster that looks like this. Now imagine I go out and I get two patients and I bring them in and I measure their performance on A and B. I might get a subject that looks like this red cross here and another subject that looks like this red circle here. If I were to look at just their behavior for parameter A, you can see that, oh, well, one subject's at plus 1.5, the other one's at minus 1.5. That's both, within normal, nothing special there. And they both actually have the same behavior in B. If I look at the RSS distance, which is how far away from zero it is, you can see that those distances are equal. So if I just look at parameter A, it looks like there's no difference between these two subjects. If I just look at parameter B, there's no difference. If I look at the task score, which is based on the RSS distance, again, no difference. But when I look at the data in this kind of plot, I can see clearly that the subject who's this red X is within normal, whereas the one with the red circle is outside of normal. Their pattern of behavior is what's outside of normal. The M distance takes this into account. And so this subject with the represented by the circle would actually end up having a very large M distance compared to the subject with the red cross. But to compare task score and M score, they're both based on distances. The task score is based on the root sum square distance, whereas the M score is based on the Mahalanobis distance. And as a result, RSS distance, all the parameters are treated equally, whereas the M score is accounting for correlations between parameters. One of the benefits of the task score is interpretability. Task scores outside of normal will always trace back to parameters that are outside of normal. So it's, if you see someone who has a high task score, you go, wow, there's something non-normal about this person's behavior. You can go back to the parameters and you will find one or more parameters that is outside of normal. So you can understand intuitively what's going on there. With an M score, that's not always going to be the case. This is, I guess, in some ways good, in some ways bad. If you're trying to understand where that large M score came from, it's not going to be obvious because the M score is detecting patterns of behavior that are abnormal. And the last distance is simply about how you access these things. Task scores are in the standard reports and exported in the CSV files, whereas the M scores are only available in the CSV files. And so in terms of summarizing those differences there, task score, easy to use capability in terms of, hey, did this subject pass or fail their performance? And as I mentioned earlier, they have a consistent meaning across different tasks in the sense that they have the same scale. But the M score, it's there, and its purpose really was to provide, as we say, a deeper investigation because it detects non-obvious patterns of atypical behavior. So if you do see something, you get some M scores that are high and they don't trace back to parameters, well, that means there's something more interesting going on. So this is a way that you can potentially detect those kinds of patterns of behavior that might get missed using either just the Z scores or just the task score. What I've talked about so far is all the numbers that we provide, but you can do more. And we've had customers who go down this path because they need to. All the raw kinematic data from these tasks, it's available, it's still there. So although we do provide all these Z scores to help you get going, you can export the raw data from Dexterity. You can then import it into something like MATLAB, and we provide tools to do that. And then you can write your own custom analysis. This is important because we've provided what we think is a lot of value based on an initial uses, but as people start expanding the way that Kinarm standard tests are used and start looking at new patient groups, what's going to happen is people will discover that, hey, there might be other parameters that are more sensitive to detecting certain abnormalities in other groups, and so people need to have that capability to dig further and to potentially find novel parameter scores. I'm not going to talk more about how you do all that. We can discuss that later if people are interested. The last thing is just some notes on KST, and that is that the references, so for the various tasks, can all be found in our user guides. If you want to know, where was this first used for doing your citation and understanding it, that's obviously there. If you want to know more details about the parameters, again, that's in our user guides. We try to provide as much information as possible so that there's a clear understanding of what parameters we have and how they're calculated and such. And the last is all of this can be found, it's in our dexterity user guide, but we also have now a subsection of that guide called the KST summary. This is posted publicly, so anybody has access to it, and therefore it's citable in your manuscripts methods section. So instead of having to rewrite what the task was, rewrite what the parameter was, and rewrite a whole bunch of things, it's probably much more efficient to just simply reference the KST summary, because then any reviewer of your paper has access to it and can go and find out that information as needed.